I dropped.
Welcome to the Applied AI podcast. I'm your host, Jacob Andra, CEO of Talbot West. I'm really excited for today's guest. She's been on the podcast 3 times. She's developed an incredible technology that has beaten a lot of machine learning benchmarks. And on today's episode, we talk about the Lumawarp model she's created, how it's beaten the benchmarks in both speed and accuracy, and some of the use cases it would be useful for in industry. Dr. Pasi, for the third time to the Applied AI podcast. It's great to have you back.
Yeah, great to be here.
So we just announced a partnership between our two companies, which I'm really excited about.
Yeah, we are too. I think it's going to be a great synergy between the two teams.
Exactly. We can help companies figure out how to apply your Lumawarp machine learning model, which is, of course, what we're here to talk about. So why don't you introduce that model, what Lumawarp is?
Lumawarp implements a new mathematical and hardware paradigm for machine learning. And, there's a lot of machine learning and AI tools out there. A lot of them are more at the application layer. A lot of them are around how do I deploy machine learning models. But then at the very foundational layer, there's this question of how do the machine learning models actually find patterns in data, right? Because that's what machine learning is all about. It's about taking data, learning patterns from it, and then applying that in new scenarios and situations. So there's a couple different factors that come into play when you're talking about how to build the best machine learning model. When it comes to the algorithms themselves, there's a couple of different dimensions of performance that are both really important in application, but often have kind of counterbalanced each other. So those two variables I would summarize as really just like accuracy and efficiency. And efficiency can be speed, it can be size. Accuracy can be measured in a variety of ways. It also includes sort of, how well does this perform under new situations? But those two broad categories are the important parts of a model, right? How good is the model? How fast is the model? And within the existing solutions for how to train a machine learning model, there's often been this trade-off between accuracy and efficiency.
So traditionally, you've had a pulley effect where if accuracy goes up, speed goes down. If speed goes up, accuracy goes down, and these things move in inverse relationship to each other.
If I was to plot, accuracy, so how accurate is this and how fast is this? Accuracy and speed on this axis like this. Well,
Okay.
then what we'll have sort of historically seen is, you might have, and I'm borrowing some of these from the quite exhaustive listing of different machine learning approaches that were put together by some of the researchers at Amazon and others involved with the TabArena benchmark. But, you might see something like XGBoost, which is, a very familiar kind of canonical machine learning algorithm, be typically very high in speed, but might be a little bit lower down in accuracy. And this is just, kind of illustrative. Whereas something like MNCA, which is actually, not one that you see as often, largely because it is so slow and so sort of computationally intensive, this might be a little bit higher in accuracy, but it comes at the cost of both inference and training speed, right? So it's a much slower, more computationally intensive model. And you'll often see, these will be towards the top of the benchmarking tests. These will be a little bit lower down, but when you look at the speed metrics, those will kind of flip. So typically, overall, that trend, when you look across all of the algorithms, will look something like, this line or a curve where as you increase the speed, you're going to be decreasing the accuracy and vice versa. So exactly this kind of pulley effect that you just described. The big innovation here is that when you look at where Lumawarp is, we are completely outside of this trend line, right? So we are able to achieve comparable speed to something like an XGBoost while having, in many cases, chart topping accuracy that is comparable to something like MNCA. The difference here is that, this took, in many cases, several hundreds of hours to train on a very large cluster. This was able to train the same data set with better performance on a gaming laptop in a matter of an hour.
Yeah, so a huge difference in speed, as you point out. Tell us about what this set of benchmarks is, kind of at a high level, and how significant this is.
Yeah, so this is a new benchmark that had been put out. It's called TabArena. It's been out since around June or July. And, really the importance of this data set is that we haven't had a particularly robust canonical benchmark for tabular learning problems. So this is one that we've been in the process of evaluating our model against. We found, of course, some really interesting results. I think sort of the primary result is the one that we've just been talking about here, where you see this disruption of this normal accuracy speed trade-off, right? So Lumawarp is able to perform at high speed while in many cases actually exceeding the accuracy of some of these largest ensembled models.
In this benchmark, there was a data set around people who had taken out HELOCs on their homes, and it was predicting who would default on their HELOC. So that's a home equity line of credit. In the data set was included who actually did default. Then you take another data set, similar but totally different people who also had HELOCs, and some defaulted and some didn't. You strip off the results of who ended up defaulting, and then you have the models predict based on that data set who defaulted, and then you compare that against the actual default rate.
So I think that's a great explanation of the problem. Very kind of typical risk prediction problem that we run into in machine learning. And one of the things that I really like about this example from the data set is that it's fairly straightforward to sort of quantify the returns on accuracy, right? So if this is like, $50,000 loan, then, you've got few thousand of these across your portfolio, a couple of percentages of an increase in accuracy can translate into several $1,000,000. What we actually saw within that benchmark is that we were outperforming the top performers.
And so, how accurate was Lumawarp?
We were topping the list on all of the different models, including many that had been ensembled and trained and tuned over the course of hundreds of hours. Again, just training these on a gaming laptop over the course of an hour. So we were able to beat the benchmark on that data set against all of these different models while still being, very accessible in terms of compute.
Yeah, so low compute, fast, and more accurate. So that seems like a winning combination to me. And it does seem like there are going to be a lot of high ROI use cases across a variety of industries where this could now be applied. Anytime you need to predict an outcome where there's a monetary value, as you pointed out, associated with higher rates of accuracy, where the stakes are high for being wrong and you really want to be as accurate as possible. I could think of a lot of healthcare applications, medical diagnostic applications, applications within the intelligence community where you need to maybe correlate signals and predict financial modeling, financial prediction, market predictions, right? You can probably think of a lot of others.
Yeah, definitely. And I think that there are many cases where, let's say, your baseline model has like a 90% accuracy. That seems pretty good for a lot of applications, but a 1 in 10 failure rate is an absolute no-go in a lot of contexts, right, that are a little bit higher risk. Whereas like a 99% accuracy, so, that 9% increase translates into only a 1 in 100 failure rate. So that is sort of like a tenfold increase in the reliability thought of that way. So, there's a number of applications where getting that improvement is actually the difference between being able to safely or strategically deploy a machine learning model versus not.
Exactly. And not only do you want it to be accurate, but you don't want to wait 500 hours and have a giant compute cluster running for those 500 hours to even get your prediction. So anytime you need low latency, immediate predictive ability.
Old intelligence is not really intelligence. It's kind of useless. After a certain point, it goes stale. And, especially when you are looking for low latency, it might be an application like robotics, or it might be something like real-time trading. The speed at which you're able to make that decision using your machine learning model and return it to the endpoint is really critical. So that latency can really matter. And even independent of that, the training time, retraining, regathering data, how efficiently you're able to do that to kind of keep up to date with the latest data is also a really important factor in deployability.
That's a really critical point. And also, I was just thinking of edge computing, where if you don't want to have to send this off to a cloud and get a response, or even in high stakes situation, if you don't want to be dependent on cloud infrastructure, you have the option to deploy this on an edge device, have it right on premises, and it'll still run. It'll be even lower latency, but then obviously even much more reliable because you're taking a lot of the complexity out of the equation.
Exactly. Well, and now this is bringing in another variable that is often related to that speed category, but I think it's worth touching on specifically, which is model size, right? Because model size is often the determinant of what types of devices you can actually put this on. So, if you're talking about wearables, in many cases, you are actually required to have a cloud connection just because of the size of those models. They don't really fit on a wearable device, or they're not able to actually inference with any kind of speed on a wearable device. And so, one of the effects of using this improved mathematical framework for machine learning is that you do get high fidelity information compression, right? And that manifests through having these smaller, faster models that maintain really the highest degree of accuracy. So better than state of the art in many of these cases.
The fact that it can just run on a tiny device, it opens up a whole new set of categories of usage that wouldn't even have been possible before. So I love that. And then, just for our audience, I think it's worth touching on that this is not even related remotely to large language models. It's an entire different branch of machine learning. You've talked at length about the unwieldiness of trying to convert large amounts of tabular data into something that large language models can consume. And I don't think you're anti-large language model. You see that they have a place in the ecosystem, as do I. You and we've talked at length about this. You've been on the podcast, now 3 times. For the purposes of this episode, give just a summary of how you see that landscape and how you see the role of Lumawarp and similar technologies kind of compared and contrasted to large language models.
Obviously, there's a lot of applications, especially those that are really close to sort of linguistic processing. But when you have data that comes in more structured form, you might even have image data, right? But basically, it's in its highest fidelity form when it's closer to that original form that the data presented itself in, rather than having to pass through this linguistic layer, right? So you're really talking about trying to take the data that is most directly relevant to the problem and putting it in that form through a machine learning model that can learn those specific patterns.
Trying to use a large language model for everything and converting all data to something a large language model can easily consume is the equivalent of forcing a self-driving car to compose a sonnet or a haiku about everything it senses on the road before it can react. Machines can consume the data in native machine formats. Why force them to convert to something that humans would understand when they can communicate much more effectively on that level? And then you introduce the large language model only where it makes sense to do so. Very excited for this partnership we have. The way I see it, you've created the world's most incredible engine, the most fuel efficient, high powered engine. We help companies assemble the car that engine can go into if they need that assembly. And so to me, it's just a perfect match. I'm so excited for what 2026 holds and what you guys have built.
Yeah, we are too. And I think that's such a good analogy. I think Talbot West does a great job at envisioning the car that can really leverage the world's most powerful engines to get people where they're trying to go.
Exactly. Well, thanks so much for coming on again. It's a pleasure as always.
Always a pleasure, Jacob. Thanks so much for having me.